Okay, so the part on conjecture for that part is you are supposed to find the y-intercept. Okay, the fx is equal to x over x plus 1. So when you want to prove the conjecture, you have to do everything all over again. Are you clear? You have to do everything all over again. You have to find the derivative first. Okay. Then, so you use quotient rule. V, this is your U, this is your V, okay? V, U prime, take away U, V prime, the whole thing divide by V squared. So this is a step whereby you have to do, okay? So this will be equal to, when you simplify, it will be 1 over x plus 1 squared. Yeah. So now what you need to do is you have to substitute the x equal to a. So you have to look for f prime a. That is 1 over a plus 1 squared. Okay, so you have to find the y-intercept for the tangent at x equal to a. So you have to put, okay, when x equal to a, so you have to look for fa first. That is equal to a over a plus 1. Okay, so you sub into the equation y equal to mx plus c. So our ulterior motive is to get the c. So now a over a plus 1 equal to m is 1 over a plus 1 squared. Your x is a. So plus c. Okay, now for this part, the c will be equal to a over a plus 1. Take away a over a plus 1 squared. So to simplify this, what you need to do is you must make sure the denominator must be the same. So what I do is I times this with a plus 1. So the top also need to times with a plus 1. Okay, so now the denominator is the same. The denominator will be a plus 1 squared. The top will be a squared plus a minus a. So that's why you have a squared over a plus 1 squared. Would that be okay? So this is a proving part. Okay, so I have done that. So now, can we go to part, okay, question 13. Okay, question 13 is talking about normal distribution, and question 13 also talk about central limit theorem. Okay, so let's revise. Let's revise about central limit theorem. Okay, let's revise central limit theorem. Okay, so there's question 13. Okay, when we talk about central limit theorem, okay, there is two parts. Okay, whether you are talking about proportions or there is confidence interval. So when we talk about central limit theorem, what you need to do is there are two things. That is sample mean or another one is sum of the sample. Okay, sum of samples. Okay, so when we talk about sample mean, the symbol is like that. And n is the sample size, okay? Okay, so when we talk about sum of the samples, the symbol is like that. So according to central limit theorem, the sample mean distribution is normal. Okay, maybe it's normally distributed, maybe it's not, depend on the sample size. So it's normally distributed. Okay, if n is greater than 30. So same go with the sum. Okay, so now, so according to central limit theorem, this sample mean, the mean of the sample mean. Okay, this is called, how do you call this? The mean of the sample mean. Okay, it will be equal to the population mean. Okay, and the standard deviation of the sample mean distribution will be equal to the population standard deviation divided by square root of n. Okay, for some of the sample, okay, when I put like that, that means this is the mean of the distribution of some of the samples. That means I can get exotic samples. So the mean for this variable, my variable is the sum of the sample. So the mean will be equal to n times the mean of the population. And the standard deviation of the sum of the samples will be equal to square root of n times by the standard deviation of the population. So these are the two main formula that you have to remember when you apply central limit theorem. Are you okay? So this will be under question 13. Are you okay? So when you sketch the graph, okay, another thing is when you sketch the graph for normal distribution, okay, so I revise a little bit, graph for normal distribution. Any normal distribution, it doesn't matter whether it's population or that one. So what you get is, you have to plot like that. Okay, the highest point will be the mean. Sorry, I'm not supposed to draw. So this is the mean. The mean is at the middle. So it's symmetrical. So mean plus one standard deviation. Mean minus 1 standard deviation. So this will be the point of inflection. Okay, then we also almost 100% sure that all the data are within 3 standard deviation away. That means the probability of X greater than mean minus 3 standard deviation and mean plus 3 standard deviation, the answer is almost equal to 1. So that's why after 3 standard deviation away, the chances of the data to be more than 3 standard deviation away will be negligible. So that's why the probability distribution density graph will be fade away. So it will go like that. So this will be your normal distribution graph. Yep. And we know that for any normal distribution graph, for any continuous variable, what is the area bounded by the curve? Area is always equal to approximately equal to 1. Because it represents probability. So if it's a higher spread, bigger spread, the graph will be lower. Okay, if it's smaller spread, the graph will be higher. So it's exactly like a rectangle. This is smaller spread. Smaller standard deviation. If bigger standard deviation, the rectangle have to go like that. So it will be shorter because the area is always 1 unit. Are you okay? So this is what you need to know for question 13. So can you please spend some time to do question 13? I believe everyone should have question 13 with you, correct? So can you please try? Okay, question 13B. Okay, the question go in this way. They say the gems are sold. Okay, in the first place, if you read the question, they say that the net weight of the gem is a random chosen jar can be modeled by a normal distribution. So that means right from the very beginning, okay, let W be the weight of jar, of gem, of jars of gem produced by that company. So this is, so jars of gem produced by that company is the population. So they say that this is normally distributed. So that means if the population weight is normally distributed, that means regardless of the sample size, the sample mean will be normally distributed. Okay, so this is with the mean of 42 gram and the standard deviation of 1.5 gram. Okay, so this is what I have for the population weight of jars. Okay, each jar, the weight is like that. Okay, so now they say the gems are sold in the jars of 24. Okay, so W24 with the bar on top. So that means this variable is the mean weight of samples of 24. Okay, so this particular variable, there's a mean weight of a sample of 24, will be normally distributed also. Okay, and according to what I said just now, part 1, the mean of W bar 24 will be equal to the population mean. Am I right? Which is 42 grams. Okay, then the standard deviation of W bar 24 will be equal to the standard deviation of the population divided by square root of 24. So you just plug it in. Okay, then you can give an approximate value here. Okay, now on the axis above, sketch the distribution. I believe everyone will know how to sketch. Am I right? Should I sketch it for you to see? Okay, so I better sketch. So this is what you have for the population. Am I right? Okay, can someone give me the standard deviation for this one? Hello, can you give me the standard deviation for this one? For the population, for the sample mean? 0.31. Thank you, 0.31. So if you look at here, 1.5 is for population, 0.31. So it's approximately 3 over 15. So it's 1 over 5. So that means the height for the one will be 5 times. Okay, 5 times. So due to space, so around here, up here, 5 times. So the graph will go like that. Okay. So you draw it properly by yourself, so the graph will go like that. I need to draw the graph so that I can explain part 3. Okay, so this is your 45 and 42. Okay, so they said part 3, will your answer to part 1 have been different if the distribution of W was not normal? Okay, I told you already, if W is not normal, then what should your minimum sample size? N must be greater than 30. Am I right? Yeah, so the answer given, someone have cut it off for me. My answer is correct. So if W is not normally distributed, then I don't expect my sample mean to be normally distributed. Will your answer to part 1 has been different if the distribution of W are not normal? Okay, explain your answer. So because it will be skewed. Okay, it will be skewed. So the answer in part 1 will be different because the sample size is not large enough. Okay? Got it? Okay, any other questions? 13E is, this is a sample. Okay, samples. I have samples. Okay, inside each box, I have 200. So each box is a sample. Are you clear? Okay, this is the box. Okay, each box is contain 200 jars. Okay, many. Okay, inside that. So they say that, so according to central limit theorem, so you can go by two ways. You can go by S200 or you can go by mean 200. Up to you. So it will be normally distributed. The mean is 200 times 45, 42. And the standard deviation here will be square root of 200 times 1.5. If you are using this, then you have to do it 42 and 1.5 divided by square root of 200. So depend on which one you are using. Okay? So they say that 2% of these boxes contain less than certain total net weight. Okay. So I can let the total weight be K. So that means I'm talking about probability of S200 2% of these boxes contain less than, so less than K. The probability is 2%. So which is 0.02. So I can do like that. So this K, I can get it by inverse norm. 200 times 42, comma, standard deviation, okay? And am I right? Or I supposed to put in the area first? I supposed to put in the area first, correct? 0.02 area first. Then I put left. Yep. So you straight away can get your K. But if you are using the mean, that means I'm talking about probability of X bar 200 is less than, because K is the total weight. So I have to find the mean weight. So K over 200 is equal to 0.02. Okay, so my K over 200 will be equal to inverse norm, same thing, but different mean and different standard deviation. Are you clear? Is that okay?